Hi class, welcome to Chemistry 252, and I'm going to be producing my own lecture videos for this course. So it'd be a good idea to watch them. We do occasionally skip over some topics in the textbook, so by watching the videos it'll give you a good idea of what we are covering and what I expect you to know by the end of the semester. So let's go ahead and start with chapter 19, and this is just an introduction to organic chemistry, and we're also going to talk about a family of compounds called alkanes. Let's go ahead and define organic chemistry. And organic chemistry is defined as the chemistry of compounds that contain carbon. So all compounds that contain carbon are considered organic compounds. Now, as a review, we know that carbon will form 4 bonds. That could be 4 single bonds. It could be a double bond and 2 single bonds. It could be a triple bond and a single bond. But it always forms 4 bonds. We refer to carbon as being tetravalent. Tetra meaning 4. So carbon forms 4 bonds. Let's take a look at methane here. We know that methane has this structural formula here. We have a carbon bonded to 4 hydrogens. And then this is the ball and stick representation of methane. As a review, organic molecules contain covalent bonds. Remember, covalent means the sharing of electrons. So they share electrons in the bonds. Organic molecules can contain both nonpolar and polar covalent bonds. So for example, we look at methane and we know that carbon-hydrogen bonds are considered nonpolar, and of course this molecule as a whole is nonpolar. We take a look here at chloromethane, and we see carbon is bonded to 3 hydrogens and 1 chlorine, and this is a polar molecule. So the carbon-chlorine bond is polar while the carbon-hydrogen bonds are nonpolar. Carbon can form multiple covalent bonds by sharing more than 2 electrons. So for example, in acetylene here, we have a carbon-carbon triple bond. In this bond, we have 3 pairs of electrons being shared for a total of 6 electrons being shared in the triple bond. If we had something like this, this is called ethene. We have a carbon-carbon double bond, so that means in this double bond, these carbons are sharing a total of 4 electrons. Organic molecules have specific 3-dimensional shapes. So we talked about molecular shapes back in Chemistry 251. You might need to review that. All right. So methane, for example, this here is a ball and stick representation of methane. This has a tetrahedral shape. We'll talk more about that in a minute. Anyway, as I said, this is a ball and stick representation. This representation here is a space-filling model. And on paper, we usually draw a representation of a molecule using a structure like this. So here we have a central carbon atom in methane bonded to the 4 hydrogens. These bonds right here are in the plane of the page, because remember, a molecule is 3-dimensional. Okay, so it's nice to be able to represent that on paper. So think of these 2 bonds being in the plane of the page, so that would correspond to this one and this one. And then this bond here with the solid wedge, this would be a bond coming out of the page, okay? So that would actually correspond to this carbon-hydrogen bond here. And then this one here with the dashed line or dashed wedge, that's going through the page. So that's away from you, and that would correspond to this one, this bond right here. This is a good way of representing the three-dimensional structure on paper of a molecule. Okay, so you're going to see these in your book. So now let's continue talking about some common bonding patterns. And we've already gone over these in Chem 251. So we know that hydrogen will always form one bond with 0 lone pairs on the hydrogen. Carbon always forms 4 and 0 lone pairs on the carbon. Nitrogen, we know, forms 3 bonds and has 1 lone pair. Oxygen, 2 bonds and 2 lone pairs, as we see here. And then the halogens, fluorine, chlorine, bromine, and iodine, form 1 bond, and we see 3 lone pairs. Remember, we can refer to lone pairs as non-bonding electrons. So many organic molecules contain hydrogen, nitrogen, and oxygen. As far as carbon-hydrogen bonds, those are always single bonds. So hydrogen only forms single bonds to carbon and to any other atom that it's bonded to. Nitrogen can form either a single bond, a double bond, or a triple bond to carbon. Oxygen can form a single or a double bond to carbon. Let's take a look at some of the properties of both inorganic and organic. Remember, last semester we talked about inorganic compounds, salts, okay, sodium chloride, magnesium chloride, sodium sulfate, and so on. So inorganic compounds like ionic compounds, salts, they have very high boiling points and melting points. Organic compounds, on the other hand, have lower melting points and boiling points. Inorganic compounds, they, when dissolved in water, if they dissolve in water, they conduct electricity. Organic compounds do not conduct electricity. Now remember, as far as those acids, they can be either strong electrolytes like hydrochloric acid or weak electrolytes like acetic acid. Many inorganic compounds, many of our salts, are soluble in water. As far as organic compounds, many organic compounds are not water soluble. Some are, but many of them are not. And what we're going to learn in this course is how to determine the properties of a particular organic substance. We'll be able to determine if they're water soluble or not. Now, functional groups are the most important when it comes to the chemistry of organic compounds. Functional group is a group of atoms, or it could be an atom, within a large molecule that has a characteristic structure and chemical behavior. So for example, this carbon-oxygen double bond is what we call a carbonyl group. And we'll talk about that a little bit later. Here we have a carbon-oxygen bond. And this one here, this would look like this as far as the functional group. And this should look familiar because this is, we see this in acetic acid, or one of the organic acids. And this is a carboxyl group. We'll talk about these a little bit later. But just know that the chemistry of a molecule is going to be primarily determined by the functional group. So a given functional group tends to undergo the same reactions in every molecule that it's a part of. So this is a table I got from another book, but there's a table similar to this in your book. The alkanes that we're going to talk about today contain only carbon-hydrogen single bonds and carbon-carbon single bonds. So we'll talk about those in depth in a little bit. Then we have alkenes, and it's a carbon-carbon double bond. The chemistry is going to take place right here in the carbon-carbon double bond. Alkyne, that's a carbon-carbon triple bond. Then we have aromatic compounds, and those have this benzene ring within them. Alkyl halides, notice we have a carbon bonded to a halogen. Alcohols, we have this OH group bonded to a carbon. You'll eventually learn all of these functional groups. You don't need to know them in this chapter. I know your book has questions about the functional groups, but we're going to go over each and every one of these as we go. So for now, just understand that functional groups do determine the chemistry of a compound. Here's that carboxyl group that we see in the organic acids. Here is what we call amide. We have a carbon that is bonded to oxygen. That's a double bond. So we have a carbonyl group. Bonded to the carbonyl carbon is a nitrogen, and we'll talk about these a little bit later. For now, just understand that these compounds are classified by functional group. As I said before, a particular functional group, no matter what molecule it's in, will undergo the same type of reactions. So here we have a small molecule. This is ethylene. That's the common name. The IUPAC name is ethene, E-T-H-E-N-E. 2 carbons. We have a carbon-carbon double bond and the 4 hydrogens. And this will undergo a reaction. It needs a catalyst, okay? I'll just put catalyst up here. We'll talk about this reaction later. This will react with hydrogen to produce an alkane. And notice what happens here. The chemistry took place at the carbon-carbon double bond. In fact, this is an addition reaction, and we see that hydrogen has been added to both of these carbons. Okay, so this is the small molecule, and here we have a fatty acid, and notice that we have one carbon-carbon double bond. Well, it also undergoes reaction with hydrogen. Again, we need a catalyst here, and the same reaction is going to take place. In other words, hydrogen will be added to each of the double bonded carbons, so that now we've gone from a carbon-carbon double bond to a carbon-carbon single bond. So first we're going to talk about reactions in small molecules. Then in the second half of the course, we're going to talk about biological reactions that involve very large molecules. But the reactions are the same because of the functional group. As we said before, organic molecules have 3-dimensional shapes. And just as a review, when we have an atom surrounded by 3 groups, okay, so in this case here, each one of these carbons is bonded to 3 atoms, 2 hydrogens and a carbon in this case. So this carbon here would be trigonal planar. Okay, so it's got a trigonal planar geometry, and the bond angles are about 120 degrees. And remember, we talked about when we have an atom bonded to 4 atoms, what we have is, in this case, the carbon is bonded to 4 hydrogens. This is methane. And we know that the carbon is tetrahedral. Remember, we have a tetrahedral geometry with each of the bonds pointing to the 4 corners of a tetrahedron. And these bond angles here are all 109.5 degrees. Again, we're going back to these 3-dimensional representations. And as I said, so for methane, we want to show that it is indeed a 3-dimensional structure. Molecules are 3-dimensional. So when drawing these structures, I would go ahead and put the carbon as the central atom. You're going to have two bonds that are in the plane of the paper. So you always want to make sure that you draw these, that they're adjacent to one another. I could also draw it this way. So these bonds here are in the plane of the paper, and then one bond is behind, okay, and then the other bond is in the front. It's coming at you, okay, it's pointing towards you. This bond here is pointing away from you through the paper, if you will. And again, if you have some models, that might be quite helpful in this course. If you have a little molecular model kit, this is how you would show that. Again, as I said before, every carbon that has 4 single bonds is going to be tetrahedral. Let's take a look at nitrogen here. We're looking at this compound here. We call this methylamine. We'll talk about amines a little bit later. I just want to show you what's going on here as far as shape goes. Let's take a look at the nitrogen here. And the nitrogen is bonded to 3 atoms, 2 hydrogens and a carbon, and it has a lone pair. Remember what happens. Its electron pair geometry is tetrahedral, but remember the lone pair, because it's only under the influence of one nucleus, whereas the bonded electrons are under the influence of 2 nuclei. Remember, that's going to compress these bonds a bit. So we say that its molecular shape is trigonal pyramidal. So what we have here is a trigonal pyramid. And then let's take a look here at oxygen. Here we have an alcohol called methanol, and we have carbon bonded to 3 hydrogens and 1 oxygen, and then a hydrogen bonded to the oxygen. Notice that the oxygen forms 2 bonds, and it has 2 lone pairs. Now, there are 4 groups about the oxygen, so its electron pair geometry would be tetrahedral, but its molecular shape, because of those 2 lone pairs, is a bent shape, just like water. And those bond angles are going to be less than the ideal 109.5 degrees. Hydrocarbons. What is a hydrocarbon? It's an organic compound that contains only carbon and hydrogen. Alkanes are hydrocarbons. And an alkane is a hydrocarbon that contains only single bonds. So carbon-hydrogen single bonds and carbon-carbon single bonds. So here is another example of an alkane. How do we know it's an alkane? Because alkanes are hydrocarbons. They contain only hydrogen and carbon, and carbon-carbon single bonds. So this is also an alkane. Now let's take a look at the first 3 alkanes. So here you recognize methane. It has 1 carbon bonded to 4 hydrogens, and this is the smallest alkane. The next one is ethane, and ethane has 2 carbons, and notice the 2 carbons are bonded to one another, and each carbon is bonded to 3 hydrogens. And then we have propane, and propane has 3 carbons, and this carbon here has 3 hydrogens bonded to it. This middle carbon, 2 hydrogens, and this other end carbon, 3 hydrogens. Our 1 carbon alkane is methane, our 2 carbon alkane is ethane, and our 3 carbon alkane is propane. I think you can see that there's only one possible way that we can arrange the carbons in methane, ethane, and propane. Now, when we get to butane, a hydrocarbon that has 4 carbons, here is the structure right here. So we have these 4 carbon atoms and bonded to hydrogens. I can draw this 2 different ways. I can draw it this way, where the carbons are connected to one another in an uninterrupted chain. So in one continuous chain. In other words, I can take my pen and I can touch all of the carbons without lifting my pencil. Now, we see this has the formula of 4 carbons and 10 hydrogens, okay? But let's take a look at this one here. We have, again, there are 4 carbons and 10 hydrogens, but notice that in this case, I cannot draw a continuous line through all 4 of the carbons. In fact, I would have to lift my pencil to include this carbon. I could also go this way. I could start from here, and my longest continuous chain is only 3 carbons. This is what we call a branch point here, okay? So the longest continuous chain here is 3 carbons. This one here, this first one, is called a straight chain alkane. So all the carbons are connected in a row in a continuous chain. A branch chain alkane, such as this one here, has a branching connection of carbons. Let's take a look at pentane. And pentane has 5 carbon atoms. This is the straight chain. I have 1, 2, 3, 4, 5 carbon atoms in the chain, and we call this pentane. Now, there are 2 other ways to draw a structure with this same molecular formula. We can draw it like this with a branch point on this carbon, or we can draw it like this where 3 carbons are in the longest continuous chain with 2 branch points on the central carbon. So these are different compounds. This one here is called pentane. This is 2-methylbutane, and this is 2,2-dimethylpropane. So different compounds, different properties. We'll learn how to name these in a few minutes. What do we call these structures? We call these structures isomers. Compounds with the same molecular formula, but different structures are called isomers. The structures that we looked at just a minute ago are a type of isomer called constitutional isomers. These compounds have the same molecular formula, but different connections among the atoms. As I said before, constitutional isomers, they're different compounds, have different physical, chemical, and biological properties. In fact, let's look at another example here. These are not alkanes. Here we have dimethyl ether and alcohol. It's ethanol, ethyl alcohol. They both have the same molecular formula, but again, I can draw the structures 2 different ways. This one is dimethyl ether, and this one here is ethanol. These are 2 completely different compounds. These are constitutional isomers. Dimethyl ether has a boiling point of a negative 23 degrees. It's a gas at room temperature, and it was used as an anesthetic at high concentration. Ethanol, on the other hand, its boiling point is 78.5 degrees at room temperature. It's a liquid at room temperature, and it's a central nervous system depressant. So these are constitutional isomers. Just for your information, there are over 75 structural isomers that have this formula. So from this alkane here, by the way, this is called decane, you can draw 75 isomers from this molecular formula here. Does that mean that all 75 exist? No. But these are possible compounds or structures. For something that has 20 carbons, we can draw 366,000 possible isomers. For something with 30 carbons, we can draw over 4 billion possible structural isomers. Again, are all these going to exist? No. And, for many different reasons. But many organic compounds have isomers. We're just talking about constitutional isomers here, but there are other types of isomers that we'll talk about a little bit later. Different ways of writing structures. You know, when you have to write a structure like this, it takes a while. Okay, it's just going to take too long, and if you're writing a paper or you have to keep drawing these structures, it's going to get quite cumbersome after a while. So what we draw, instead of structural formulas, we draw these condensed structures. And it's just a shorthand way of drawing structures in which the carbon-carbon single bonds, or I should say carbon-carbon bonds, and carbon-hydrogen bonds are understood rather than shown. So in other words, here's butane, and rather than show the single bonds between the hydrogens and carbon and between the carbons, it's just understood that they're there. We would write the condensed structure for butane this way. For 2-methylpropane, we have the condensed structure. For octane, here is the condensed structure, but you can see that the more carbons, even the condensed structures, can take a while to write. So we can condense them even further to this. So for example, we start at the left. It's just like reading a book. We start at the left. So here's our CH3. And then we have 1, 2, 3, 4, 5, 6 CH2s, or methylene groups as we call them. So what we do is we put the CH2 in parentheses and a subscript of 6, and then finally the CH3. We also have what we call line structures. So let me show you how to draw a line structure. We'll draw hexane. So 1, 2, 3, 4, 5, 6. Let me just erase that. This 2 here, it looks more like a 3. We don't want that there. All right, so here we have hexane. That's an alkane with 6 carbons. So I'm going to draw the line structure. So I start again. I go from left to right. So here we have the CH3. So that would be here. And then we have 1, 2, 3, 4 CH2s. This would be the first one here. 1, 2, 3, 4, and then a CH3. This corresponds to the CH3. Where there's 2 intersections, those correspond to the CH2s. So we have 1, 2, 3, 4, and then here would be the CH3. So that's how we draw line structures. Let's go ahead and draw a line structure for, where is it? 2-methylpropane. Okay, so let me draw out the 2-methylpropane. So we have okay. All right, so let's go ahead and draw this as a line structure. We have our CH3, and then our second carbon. Let's go ahead and draw the main chain first, okay? So we have this second carbon, and then the third carbon here, but then we have to draw, you want to assume that there are enough hydrogens around each carbon to give it 4 bonds. And then you draw in all the other atoms and hydrogens that are directly bonded to them. So make sure that you know how to draw line structures. In fact, let me move this over here. Put this in here. Okay, so let's go ahead and draw the line structure for this. Again, let's start with this main chain of 1, 2, 3, 4, 5, 6, 7 carbons. Okay, so 1, 2, 3, 4, 5, 6, 7. So 1, 2, 3, 4, 5, 6, 7. And then here on carbon number 1, 2, on this one here, I have a CH3 group. And then on this one, I also have a CH3 group. Okay, so these two lines here correspond to these two CH3 groups. Here's my CH3, CH2, CH2. This is the CH, and then here is the CH3. Here is the other CH. This is the CH3. Here's a CH2, and then the CH3. So those are line structures. You're going to see both line structures and structural formulas and condensed structural formulas in this course. So make sure that you can draw line structures. Now, let's go ahead and draw these as condensed structures and line structures. So pentane, that'll be easy. It's a straight chain. It has 5 carbons. So start here. That's 1, 2, 3, 4, and 5. So that's pentane. And you can check 1, 2, 3, 4, 5. That was easy. Let's go ahead and draw 2-methylbutane. And, oh, they also wanted condensed structures. Okay. So reading from left to right, I have a CH3. Here I have a CH2, CH2, CH2. So let's put those in. That was 3 CH2s. And then here a CH3. So the condensed and the line. Let's do 2-methylbutane. And what I'm going to do is just find the longest continuous chain, which is 4 carbons. And I know that because of the name, butane. That's a 4-carbon alkane. We'll talk about naming in a little bit. So I'm going to start from left to right again. So we'll start with this carbon. I have a CH3. And we'll go to this one. That's a CH2. And then this one here, we just have a CH. And we have this methyl group here coming off the carbon. So I can write that like that. And then finally, this CH3. And then we draw the line structure. That's easy from the condensed formula or from the structural formula. So my CH3, here's my CH2 up here. And then I have the CH. And then the CH3. And I have the methyl group coming off of the CH. Okay, let's do the 2,2-dimethylpropane. Again, I'm going to find my longest continuous chain. I can either go this way or this way. I'm just going to go this way. I'll read from left to right. So I have my CH3. And then this middle carbon here, I have 2 of these CH3s branching. So I have to draw the branches. That way we know where they are and what those branching substituents are. And then I have the CH3. So that's the condensed structure here. And let me see here. Let me show you another way that I could write this condensed structure. I could write it like this. Okay, I could write it like that. So we already know that the carbon atoms in alkanes have 4 bonds pointing out towards the 4 corners of a tetrahedron. So what that means is each one of these carbons in an alkane is bonded to 4 atoms and therefore are tetrahedral carbons. And there is what we call rotation about carbon-carbon single bonds. So if you were to build a model like this, all right, and what you can do is you can rotate it many different ways, okay, because you're rotating about the carbon-carbon single bonds. If you were to do that, you could rotate it to where this side comes up a little bit or a little bit more or a little bit less. But there's an infinite number of possible 3-dimensional geometries, and we call these conformations. And a conformation is the specific three-dimensional arrangement of atoms in a molecule. So we could go into this much further, and I think your book might, but all you need to know is that most molecules are going to have the least crowded conformation. You look at this here, and this is pretty crowded. You have these two methyl groups that are very close to one another, and there's going to be repulsions there, and the same here. But here, the groups are as far away from one another as possible. This is going to be the most stable state. So at any time, most of the molecules are going to be in this conformation. All right, so conformation does not change structure. It's just the three-dimensional arrangements. And again, I think that's all you need to know for this course. If this was an organic chemistry course, then we'd certainly get into a lot more detail. Okay, got a question for you here. Are the following pairs the same molecule? Are they isomers or unrelated? Let's look at these in A. So what's the first thing you need to do? Let's look at the molecular formulas for each. So this one here, we have 1, 2, 3, 4, 5, 6 carbons, and we have 3, 5, 7, 8, 11, 12, 13, 14 hydrogen. Let's check this one. 1, 2, 3, 4, 5, 6 carbons, and 6, 7, 8, 9, 10, 11, 14 hydrogens. Okay, so these have the same molecular formula. So they're either the same or they're isomers. Whether or not they're the same will be dependent on where the branch points are. So let's take a look. Let's find the longest continuous chain for each of these. Well, these carbons here are in the longest continuous chain. That's 1, 2, 3, 4, 5 carbons in the longest continuous chain. And we have this branch point here on carbon number 2. Okay, well, guess what? The longest continuous chain here, 1, 2, 3, 4, 5 carbons, and this branch point is on carbon number 2. These are the same. They are not isomers. Let's take a look at B. Again, let's check the molecular formula. So 1, 2, 3, 4, 5, 6 carbons, and 3, 5, 6, 9, 10, 11, 14 hydrogens again. Okay, so what do we have here? 1, 2, 3, 4, 5, 6 carbons, and 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 hydrogens. Okay, so now we need to check these branch points. So the first thing I'm going to do is find my longest continuous chain. And I can do that here. 1, 2, 3, 4. But I think we can get 1, 2, 3, 4, 5 carbons out of this. So if I were to start here, I'd have 1, 2, 3, 4, 5 carbons in my longest continuous chain. And here I have a branch. And that would be on carbon number 1, 2, 3. So 5 carbons in my longest continuous chain, and on carbon number 3 I have a branch point. Let's see what's going on here. My longest continuous chain here, I can go 1, 2, 3, 4, 5, or I can go 1, 2, 3, 4, 5, but I'm going to go this way, or I could even go this way, 1, 2, 3, 4, 5. So let me just start here. We'll make that number 1. 1, 2, 3, 4, 5. Remember, you can find that continuous chain from different ends of the molecule. So it might be a little different. That's one longest continuous chain. Another way I could do that on here would be this way. 1, 2, 3, 4, 5. Okay. But either way, my branch point is on carbon number 2. In this case, my branch point was on carbon number 3. So these are isomers, because the branch point is on a different carbon. Both have 5 carbons in the longest continuous chain, but the branch points are different. They're isomers. Now this one here, again, I always check the molecular formula first. So here we have 3 carbons, and we have 3, 5, 8 hydrogens, and we have 1 oxygen. Here we have 1, 2, 3 carbons. We have 5, 6 hydrogens. I can stop right here. The molecular formulas are different, so these are non-related. That's the end of this video. In the next video, what we're going to do is work on nomenclature, and then there'll be one more video for this, and that will be on the cycloalkanes. Everybody have a great day.